Hey, what's going on, guys? Gomakakins here. In this video we're gonna finally start implementing our board variables, like the set of bitboards to represent the board positions, the board position, and the set of variables to represent the board state. Actually, things like side move, castling rights, and in peasant square, and also some additional enumerations to make it easier. Implementing like functions like printboard and parse FEN to convert piece encodings to ASCII characters back and forth. But before we start doing this, let me just first try to mention one important update within the source code. A guy named Harold from talkchess.com forum kindly pointed out that I had an unsafe macro definitions right here within the bit manipulations section. So the idea is that if the source of this bitboard argument being sent into the macro would be not the single variable or constant, but some sort of an expression, in theory it could lead to some sort of a wrong outputs when this expression is about to get evaluated. So the idea is to enclose all the arguments within the parentheses to make it safe. So just simply to make sure that if bitboard is not 0 unsigned long or 1 unsigned long or some variable representing occupancies or something, but some sort of an expression, just to make sure that if this expression would have been evaluated first and then everything else. And the same for the squares. Obviously we're not even gonna be ever using this using any expressions to calculate the square, but still it's really kind of more safe way of doing things when when it comes to the macros, basically. So just to bear that in mind. And from now on, actually, we can already go for our board variable definitions part. So here I've created a schema for you guys to easier understand how exactly the bitboard board representation works actually. So let me first quickly walk through this schema, and then we'll go defining our board variables. So if we have the altogether board position, it looks quite pretty simple and well known. So this is the starting position of the game of chess, and here we have white pieces and the black pieces. But when it comes to bitboards, we need a single bitboard or unsigned long 64-bit number integer to represent every single piece type of every color. So we need up to 6 bitboards to represent white pieces, because it goes like for white pawns, white knights, white bishops, white rooks, white queens, and white king. Up to 6, and the same for black pieces. And here I'm providing the visual representation of these bitboards and how they would look like in binary in case of the starting position. So let's consider the white pieces, and here we have up to 6 bitboards representing all the white pieces. So we have the bitboard for white pawns, and we have all the white pawns being set up on the appropriate squares. Then we go for knights. Knights are set up on b1 and g1 respectively. Then we have the bishops, then we have the rooks, queen, and king. And absolutely the same, but just from the other opposite side of the board, we have this bits being set up for black pawns, black knights. So here we have the list of black pieces, black bitboards, king, knights, bishops, rooks, queen, and king. This is it. And also we want to keep tracking of 3 additional bitboards regarding to occupancies. So we'll have the bitboard having only white occupancies, here only black occupancies. So these two would have been needed in order to distinguish between the white and black pieces when it comes to the captures, to generating captures within our move generator. And also within the square attack function, to make sure that well, probably not in square attack function, but in the move generator, definitely, because you remember, like, our piece attack tables don't take into account things like the color of a blocker. It just drops for sliding pieces, they just drop the attack race when it comes to the occupancy regardless of color. So we will also need to distinguish between white and black occupancies in order to answer the question whether current given site can actually capture the current piece or not, based on whether it's the same color or the opposite color. And also we'll have we would be keep tracking of all occupancies bitboard. So this bitboard represents all the pieces regardless of type on a chessboard. So this would have been needed additionally as well. And if we just gonna map all this stuff together, we'll have eventually we will have our chessboard looks like this. And this is the exact output from the printboard function that we're supposed to be writing probably in the next video. I'm not sure yet. Well, okay, so let's go for defining all these data structures we need, and then we'll go for defining some additional structures as well. So I just want to make sure that the code still compiles and runs after I've been adding these commentaries and changing the macros. So if I just say make debug, and if it compiles, just run BBC binary executable. Yeah, it works. So yeah, also I have removed all the stuff from the previous execution, like defining the occupancy bitboard and attacks for sliding pieces. Okay, so the very first variable to define here would be the bitboards themselves. So define bitboards, and the way I'm doing this is in a form of an array, because it's easier to loop over this the array of bitboards, just more comfortable way of doing things. So I can simply say use64 type, which stands for unsigned long bitboard type, and call the variable bitboards, and there would be up to 12 elements there. And assuming this is the global variable, we don't really need to initialize this, because global variables are by default are initialized to zeros, well, at least assuming if you're using the GCC compiler. And the next thing, we need to define occupancy bitboards, occupancy bitboards. So here, let's say define piece bitboards, and here define occupancy bitboards. So use64, and I call this occupancies, like this, and there would be up to 3 elements. So first for white occupancy, black occupancy, and all occupancies. And also you remember we have the enumeration for sites. So here we have white, black, and also I will add another constant here called both. So just to make it easier referencing the occupancy for all the pieces. So we'll be using this to reference white occupancies, this one to reference black occupancies, and this to reference like both occupancies. Okay, so the next thing we also need to keep track of. Well, let's actually I just don't really want this defined keyboard here. So piece bitboards, occupancy bitboards. Here we have the site to move. So let's call this integer site. Well, we can actually initialize this to white, but it doesn't matter, because anyway we would be initializing this site within the parse function, because that would be the only legal way of starting whatever calculations. So in site to move, also we need to keep track of in peasant square, in peasant square, oh my god, in peasant square, in peasant. And by the way, I'm just wondering, did I already define the no square within my... Okay, probably I didn't. So let's actually define the no square. And actually to make it even more safe, I would probably initialize the site to -1. So this is the illegal site, and in peasant I would initialize this to no square. which is obviously kind of off board. Okay, so and also we'll need to define our castling rights. So castling rights variable here. So int castle, and it would be equal to, well, actually I'm not going to be initializing this. Yeah, it should be 0 by default. Okay, and now let's go for defining the castling bits. I already created a little schema here as well. So castling bits, and I just want to enumerate the following constants. So we'll have white king castling and black king white king castling, black king castling, and oh sorry, what am I talking about? So we need, okay, let's start from the explanation and then go to the definition. So there would be up to 4 bits, and if the bit is flagged, that means that so in case if the first bit is flagged, this means that the white king can castle to the king side. In case if this bit is flagged, this means that the white king can castle to the queen side. Here the 4th bit is being turned on, black king can castle to the king side, and here black king can castle to the queen side. And I'm just looking for proper definitions for this with this constants. So white queen side, white king side. Well, probably I can even though these are the constants, but probably I will make them lower cases. So white king side castling, white queen side castling, then black king side castling, and black queen side castling. And this would be equal to 1, this would be equal to 2. So I'm just using this decimal representation of this binary strings here. So this would be equal to 4, and this one would be equal to 8. So if you've been following the legendary Chess Engine in C series by Blue Fever Software, this is literally the same thing like how he does in his series. So nothing really new here. Okay, so the next thing to consider, I would like to enumerate the some sort of a piece encoding, basically. So let's say just wondering where better to put this. Encode pieces. Okay, and give another enumeration here. So I would be using the standard ASCII characters to represent the pieces as they used when we're printing them to screen, but here I would also like to use them as the constants. So we have uppercase letters for representing white pieces, and lowercase letters representing black pieces. So we'll have like pawn, knight, bishop, rook, queen, and king for blacks, and also pawn, knight, bishop, rook, queen, and king for black pieces. Okay, so that's probably better put the commentary here. So I hope it's clear that, oh my god, what have I done? No. So that this part regards to this castling rights, or, well, okay, maybe I just better put this piece enumeration somewhere else. So yeah, maybe just put it right over in here. Okay, and now we also need a couple of variables to represent the pieces in ASCII format, in Unicode format, and also take care of conversion the ASCII pieces back to this encoded constants. So let's start with the very beginning, basically. So here I want to define ASCII pieces, and this would be the character pieces. I'll actually call this ASCII pieces. So that would be slightly bit different output regarding the it would be slightly bit different output on different operating systems. So I have no idea how to print Unicode on Windows, so I would be printing Unicode characters only on Linux, in Linux version of this engine. But on Windows it would be printing ASCII characters, not Unicode characters. But on Linux, again, like, it would be printing this like pretty characters we have here. So but first let's go for our ASCII pieces, and it would be equal to so we have again like pawn, knight, and again the index. So you know, like that in C programming language, the string is considered to be as the array of characters, where every character has its own index. So we can use this piece codes in order to as an indices to reference this array. So if we just reference the ASCII pieces, if we just reference the ASCII pieces array by the index of white pawn, which equals to 0, so this is like 0, 1, 2, 3, 4, etc. So it would return us return this ASCII P number here. Okay, so pawn, knight, bishop, rook, queen, king, right? 6. Okay, and black pieces pawn, knight, bishop, rook, queen, and king. And now I want to define the Unicode pieces as well. So Unicode pieces, we will be making use of this during implementing the print bitboard, the print board function, gathering all the bitboards into one and finally trying to print the board position, how it is actually. Okay, so Unicode pieces, and this would be character pointer to the array of strings, array of pointers actually. So Unicode pieces, and this would be equal to, well, by the way, we can also specify the number of how many characters we have in this array. So it's kind of 12, so we can say like this. So ASCII piece is 12, and here we have 12 pointers. Every pointer would be pointing to the beginning of this of the Unicode character, which is which occupies more bytes than this character is, so treated to be as a string in C programming language. Okay, so I can simply say like this, and 1, 2. So just make it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now I just want to initialize them. So let me grab this part. So starting with the white pawn, and then knight, and then the bishop. Okay, bishop, rook, queen, and king. And then going for black pieces, so starting with the pawn, and then knight, and then bishop, and then rook, and queen, and finally king. Okay, so this is it. And we will also need one more variable. So when it comes to parsing the FEN string, we would encounter this like ASCII characters that would be represented the actual pieces on board. So we would also need to convert those characters to this like encodings to later on index the array of bitboards right over in here, this bitboards. So to make this a little bit easier, we need to define, just don't remember how to call the variable, our character pieces. So let's call this let's say character to encoded constants, like this. So convert ASCII character pieces to encoded constants, and I just grade this integer. Let's call this character pieces, and this would be equal to the following stuff. So you know, like in C programming language, the characters are the same integers basically, so we can use them as indices, and we can say, so the pawn would be equal to this pawn, and knight would be equal to knight, and rook would be equal to rook. Oh, sorry, first bishop, first bishop, like this, and then queen like this, and king like this, and then the same but for the black pieces respectively. So pawn, knight, bishop, rook, queen, king, and here pawn, knight, bishop, rook, queen, and king. Okay, so I just want to make sure that all this stuff still gonna compiles and runs, and let's have a look. Okay, no square, and so something is wrong. Oh, obviously I don't need the semicolon there, and something wrong. Oh, yeah, it's a bit not what I meant actually, like this. So now it should work. Okay, perfect. So now let's go to some tests. So we don't have any pieces being set up on our bitboards, but we can actually try that. So what I want to say is simply like, if you just take let's use our set bit macro and take bitboards indexed by the white pawn, and I want to set I want to set a bit there at the square of, say, e2. So if we just now print the bitboard and using our bitboards indexed by white pawn, then it should print as a bitboard containing the one being set on this e2 square. So the idea is very simple, just like I've been already mentioning. So we're using these constants to index the bitboards. This is quite pretty simple, and we're just using this encodings, this encoded piece values in order to index the list of our bitboards. That's kind of it. Okay, so let's go for some sort of another test. So well, here I just say set pawn, set white pawn on e2, and here we just print white pawn bitboard. Okay, and also we can let's say print piece. So if we just want to print the piece that is available on this Y pawn bitboards on the E2 square, so we can simply say like printf and then let's say piece. And well, this would be different on Windows and on Linux, and I would be covering this when it comes to implementing the print board function. But probably I can already show you this now as well. So for characters, we need this sort of a specifier, and we can simply say bitboards indexed by the white pawn, and we want to get bit from here, and or hold on a sec. No, it's not exactly. So yeah, we don't actually need to get something from there, at least for now. We can simply say ASCII pieces indexed by the white pawn like this. So let's have a look. So we have this pawn being printed, and if we want to print the Unicode version of this, we need to say, well, let me just copy this, and here we already need to use the string specifier and already the Unicode pieces like this. But if you're on Windows, this won't work for you. So that's the reason why I keep track of two possibilities, and we would be using this like stuff. So we can say if def win64. In this case, we would be printing this version, and else we would be printing this version. So and if making use of this C preprocessor macros. So sorry. Oh, so you see, like it recognizes that I'm on Linux and prints only the Linux version. But if we just try to run the same code on Windows, well, actually, let me add this get character in order to avoid Windows emulator escaping immediately. And if I just open the folder here and try to run this bbc.exe, oh, not like this, sorry. Wine. I'm using Wine in order to run Windows programs on Linux, and it's a bit weird why this is so slow. Okay, but anyway, what I wanted to show you, that on Windows it would be printing this ASCII character instead of Unicode character. So just feel the difference. So here in Linux we have this Unicode characters, and on Windows we have this ASCII characters. I know that most of Chess Engine developers actually don't really like to use Unicode characters and prefer using this ASCII characters, so it's literally on your own, whatever piece representation do you prefer. Okay, so no need to go there anymore. So what else? Well, also we can make another little test here. So we can, let's print f. So let's say we have our character pieces array being indexed by, say, this y pawn that we would be taken, let's say, from the FEN string one day. And well, let's first try to, so this would be the decimal, right? So piece and the decimal, and it would oh my god, no, not make fall, please. It would now actually print 0 because y pawn is encoded as 0. Let's say like kin here, y kin, it prints this piece code, and now we can use this. This is equal to the piece code. So again, we can just print some sort of like let's say ASCII pieces, and we just use this piece code here that is converted from the character to the piece code, and now it would be printing the big K. Oh no, it's 75 because I'm printing the decimal, not the characters. So to make it a character, I need to make it like this. So now it prints K. So let's drop this back here, and also for Linux I would like to make it this way. So Unicode and the string specifier, and this should work. So we have the skin. So what we've done here, we've just taken the ASCII character representation of a white king, taken, let's say, from the FPN string, and then we've converted this to the piece code, which is equal to 5, and then we did index the Unicode pieces array by this encoded piece value in order to get the human readable representation of a white king in the console. Well, okay guys, so this is it for this video, and this sort of variables we've already defined are quite pretty essential. There would be a little bit more variables to define along the way, but I would be adding them as necessary. And yeah, so it's gonna Caslin I didn't even, okay, so just Caslin writes encoded as bits, or better, Caslin writes binary encoding. This is better. Okay guys, so I guess, yeah, now this is really it. So starting from next video we'll go for printing our board, and then we'll go for parsing the FN string. Yeah, that's the plan, at least how I can see it at this particular moment. So thanks for watching, thanks for following. I appreciate your time being spent on trying to dig into this series. This really means a lot to me, guys. I'm really grateful to you for this, and hope to see you in the next video. Until then, and take care.